So we already finished the star connected and the delta connected loads. Now we are going to discuss the power factor improvement and the power factor correction equipments. So for the power factor improvements, so the heating and lighting loads supplied from a three-phase supply have power factors ranging from 0.95 to unity. But motor loads have usually low lagging power factors ranging from 0.5 to 0.9. Single-phase motors may have as low as 0.4 power factor, and electric welding units have even low power factors of 0.2 or 0.3. So from our given formulas, the power factor is given by cosine theta, that is equal to kilowatt divided by kVA, or the kVA equal to kilowatt divided by the cosine theta, or the power factor. In the case of a single phase supply, kVA is equal to VI, or the voltage, multiplied by the current divided by 1000, or I is equal to 1000 multiplied by kVA divided by the voltage. Therefore, we can see in the formula that the current is directly proportional to our apparent power, which is the kVA. In case of a three-phase supply, kVA is equal to the square root of 3 VLIL, or the line voltage, times the line current divided by 1000, or our line current is equal to 1000 times kVA divided by square root of 3 times the line voltage. Therefore, we can say that also the current is directly proportional to our apparent power. In each case, the kVA is directly proportional to current. The chief disadvantage of a lower power factor is that the current required for a given power is very high. So, if our current is very high, of course, it can affect also the sizes of our conductors. So, pag mas malaki yung current mo, mas malaki din yung diameter ng mga conductors mo. Of course, if you have a larger diameter of conductors, it is much expensive. So this fact leads to the following undesirable results. The first one is large kVA for a given amount of power. So all electric machinery like alternators, transformers, switchgears, and cables are limited in their current carrying capacity by the permissible temperature rise, which is proportional to I squared. Hence, they may all be fully loaded with respect to their rated kVA without delivering their full power. So obviously, it is possible for an existing plant of a given kVA rating to increase its earning capacity, which is proportional to the power supplied in kilowatts if the overall power factor is improved such that it is being raised. So for us to have a lower power factor, there are ways to improve or raise the power factor. The second one is poor voltage regulation. When a load having a low lagging power factor is switched on, there is a large voltage drop in the supply voltage because of the increased voltage drop in the supply lines and transformers. This drop in voltage adversely affects the starting torques of motors and necessitates expensive voltage stabilizing equipment for keeping the consumer's voltage fluctuations within the statutory limits. Moreover, due to this excessive drop, heaters take longer time to provide the desired heat energy. Fluorescent lights flicker and incandescent lamps are not as bright as they should be. Hence, all supply undertakings try to encourage consumers to have a high power factor. The following equipment is generally used for improving or correcting the power factor. First one is the synchronous motors or the capacitors. So these machines draw leading kVAR when they are overexcited and especially when they are running in idle. They are employed for correcting the power factor in bulk and have the special advantage that the amount of correction can be varied by changing their excitation. The second one is the static capacitors. They are installed to improve the power factor of a group of AC motors and are practically loss-free, such that they draw a current leading in phase by 90 degrees. Since their capacitances are not variable, they tend to overcompensate on light loads unless arrangements for automatic switching of the capacitor bank are made. So the third one is the phase advancers. They are fitted with individual machines. However, it may be noted that the economical degree of correction to be applied in each case depends upon the tariff arrangement between the consumers and the supply authorities. So nakadepende kung ano yung pinagkasunduang power factor ng consumers and also the distributors. Mas maganda yung power factor na close to unity power factor. Kasi hindi nasasayang yung power na ginagamit. Kung mas malaki yung theta natin, mas lower yung power factor. Let's have an example. A 3-phase 37.3 kilowatts, 440 volts, 50 Hz induction motor operates on full load with an efficiency of 89% and at a power factor of 0.85 lagging. Calculate the total kVA or the apparent power rating of capacitors required to raise the full load power factor of 0.95 lagging. What will be the capacitance per phase if the capacitors are in delta connected and in star connected? So we have a motor, this one, and it has an output power of 37.3 kilowatts and at 440 volts line to line. So what will be the kVA rating of the capacitor required for us to correct the power factor from 0.85 to 0.95 lagging? So this one is in delta. So i-redraw lang natin to in Y para ma-solve natin yung letter B. And it is connected to a 3-phase supply. Now, of course, first we must compute the input power dito. To do that, we have efficiency equal to output over input times 100%. That is P input equal to 37.3 kilowatt divided by the efficiency, 0.89. That is 41,910.11 watts. We have two conditions here for the power factor 1 and also for the power factor 2. Solving the theta of the power factor 1, that is arc cosine of 0.85, that is 31.788 lagging. Para makuha natin yung VAR or the reactive power, that is Q, kailangan natin ng power triangle. So this is our power triangle. The x-axis is of course our output power or the power, true power. Y-axis is our Q or reactive power, and the hypotenuse of the triangle is the apparent power. So, ito yung Q ng power factor 1 natin. So, this is the theta 1 or the phi 1, and this is its K var or the Q. Q is the var. For theta 2 or phi 2, ito naman yung K var ng theta 2. Also, its apparent power is for K var 1, this is the apparent power S kVA 1, and for K var 2, this is the apparent power kVA 2. So, ano yung value ng capacitive or capacitor natin para tumaas yung power factor natin from 0.85 to 0.95. So, para makorek natin yung power factor, of course, the value here will be the same as the value in your upper. To do that, this K var here, QC, let's say QC, that is the difference between your K var 1 and your K var 2. It is Q1 minus Q2. But first, we need to solve for Q1 and Q2. So, for Q1, we have motor for Q1, that is the power tangent of theta. TOA, so opposite over adjacent. So, that is equal to Q P tan theta 41,910.11 multiplied by the tangent of 31.788, that is 25,973.211 bar. For power factor 2, we have 0.95, that is 18.195 degrees. And Q2 is P tan theta 2, that is 41,910.11. Tangent of 18.195 equal to 13,775.29 var. So, the difference in the values of K var is due to the capacitors which supply leading K var to partially neutralize the lagging K var of the motor. So, para makompensate yung lagging power factor dito, kailangan natin ng value ng K var dun sa taas. Ito. To do that, we need to get the difference of your Q1 and Q2. That will be equal to 12,197.929 var. So, since capacitors are loss-free, their reactive power is the same as the apparent power. Therefore, the apparent power per capacitor is equal to 12,197.929 divided by 3, since this is a 3-phase. So, our apparent power per phase now is 4,065.976 volt ampere. So, in delta connection, we discussed earlier that the phase voltage is equal to the line voltage. Getting now the current, that is apparent power equal to per phase voltage times the per phase current. So, S phase divided by E phase equal to 4,065.976 divided by our voltage, that is 440, equal to 9.241 amperes. That is our current. Solving the value of capacitive reactance, XC, from Ohm's law, that is E phase divided by I phase, equal to 47.614 ohms. Solving now the required, which is the capacitance. C is equal to 1 over omega C equal to 66.85 microfarad. So that is for delta connection. The second one is in Y connection. So line voltage is equal to square root of 3 times the phase voltage. So phase voltage now is 440 divided by square root of 3 equal to 254.034 volts. So S phase equal to E phase, I phase, solving your current, that is 16 amperes. Again, same procedure. From Ohm's law, XC is equal to E phase divided by I phase. That is 254.034 divided by 16 equal to 15.877 ohms. The capacitance now will be C equal to 1 divided by 2 pi F times the value of your XC equal to 200.45 microfarad. So this is the value of your capacitance per phase when it is connected in Y connection. Para maging 0.95 yung power factor natin. From 0.85, lagging power factor, it was raised by capacitor to 0.95 power factor lagging. So, nag-improve yung power factor natin. Next example, we have 3 impedance coils, each having a resistance of 20 ohms and a reactance of 15 ohms, are connected in star to a 400 volts 3-phase 50 Hz supply. Calculate the letter A, the line current, B, the power supplied, and C is the power factor. If three capacitors, each of the same capacitance, are connected in delta to the same supply so as to form parallel circuit with the above impedance coils, calculate the capacitance of each capacitor to obtain a resultant power factor of 0.95 lagging. So we have here the circuit diagram. We have a load of Y connected or star, and it has a per phase impedance of 20 plus J 15 ohms. So may 20 plus J 15 dito, 20 plus J 15, 20 plus J 15. And before we calculate the capacitance of this capacitor which is connected in parallel with the Y, we need to calculate first the line current, power supplied, and the power factor of this Y connected load. To do that, so before capacitors are connected, we know that in Y connection we have the line current that is equal to the phase current, and the line voltage is equal to square root of 3 phase voltage. And phase voltage now is equal to 400 divided by square root of 3, that is 230.94 volts. Solving now the required letter A, that is the line current. So IL is equal to I phase, that is equal to E phase divided by Z phase. 230.94 divided by 20 plus J 15, that is 9.238, angle negative 36.87 degrees amperes. For letter B, for the power, total power of the Y connected load, we have square root of 3 ELIL cosine theta. That is 5,120.212 watts. And for the power factor of the system, we have cosine of course, this is its power factor, 36.87. That is 0.8. And since this is an inductor, the direction of the angle is lagging. This is the vector diagram of our Y connection. This is our theta 1, and this is the var or the Q. And this is its parent power, S. And this is the true power, P. And now we are going to connect a delta connected capacitor for us to improve its power factor from 0.85 to 0.95 power factor. We will solve the var of the capacitor that is useful to correct its power factor. We need to solve the var 1 and var 2, and the difference of these two is the reactive power of the capacitor, of the whole capacitor. So this is the formula. When capacitors are connected, the theta 1 is the arc cosine of 0.85, that is 36.87 degrees. And theta 2 is the arc cosine of 0.95, that is 18.195 degrees. Q1 or the var 1, we have square root of 3 ELIL sine of 36.87. Or we can solve this one by P tan theta 1. Q1 is equal to 3840.16 var. While the Q2, given that 0.95 power factor, we have P tan theta 2, 5120.212 tangent of 18.195 equal to 1682.945 var. Getting the difference of the Q1 and Q2, that will be the var of our capacitor. So the difference is 2157.215 var. So since capacitor is lossless and it does not absorb power, we can say that the reactive power of the capacitor is equal to its apparent power. So QC is equal to SC. SC now is 2157.215 volt ampere. And we will going to solve the capacitor, the apparent power per capacitor. That is 2157.215 divided by 3 equal to 719.072 volt ampere. So this is now our apparent power per phase. So for delta connection, i-connect na natin yung capacitor na naka-delta, and we know that the phase voltage is equal to line voltage and line current is equal to square root of 3 I phase. From this one, the per phase value of our apparent power, we can calculate your per phase current. So S phase divided by E phase equal to 719.072 divided by our voltage, which is 400 volts. That is equal to 1.798 amperes. The value now of our reactance, capacitive reactance XC is equal to E phase divided by I phase, equal to 400 divided by 1.798, and that is 212 or 222.509 ohms. Getting now the value of the capacitance per phase of the delta connection. So per phase yung kinukuha natin, that is equal to 1 over omega XC, equal to 1 over 2 pi times the frequency, 50 times the XC, 222.509. This is now the value of the capacitor. Capacitance of the capacitor, 14.305 microfarad. So 14.305. So eto siya, 14. C is equal to 14 point something, C is equal to 14 point, C is equal to 14 point something. So this is now the value of the capacitor, which will improve the power factor of the system.